So I'll now come to the other open addressing technique. So we looked at linear probing. Linear probing, we compute the hash function, we look at that location, next location, and so on and on. In double hashing, what we do is we have two hash functions, h1 and h2. h1, the value of h1 gives me the first position where I am going to look for that key k. Okay, and then h2 of k will tell me the offset from the first position where I am going to look again for the key k. Okay, so let's look at this piece of code. So probe is set to h1 of k, so that's the first position I look at, and offset is set to h2 of k. First, I'll just look at the probe, the location specified by probe in the table. If it is occupied, then the next location I'll look at is probe plus offset. Probe is set to probe plus offset, which means this is the next location I look at. Right? If this is also occupied, then the next location I look at is probe plus offset, where whatever, or probe plus offset, right? So which means that offset is determining key with how much distance I am going to advance every time I don't see the element that I am searching for. Right? So if you look at linear probing, for linear probing your offset was always of 1, right? You were always just going to the next location. So that corresponds to an offset of a 1. If I went, instead of to the next location, I went to always jump one location ahead, as in jump 2 locations, so then offset would have been 2, and so on. So offset, and this offset in this case is determined by this hash function h2. So this offset could be different for different keys. Yeah. Okay. So we'll look at we'll soon see an example of how double hashing works. If m is a prime, then this technique will ensure that we look at all the locations of the table. So in linear probing, because the offset was 1, we would look at all the locations in the table. If there was an empty location, we would always be able to insert the element. Right? Now we would not like that the following happens, that there are empty locations in the table, but you start from a certain location and then you go, let's say 3 units, offset is 3, so you go 3 units ahead, and then you go 3 units ahead, and you go 3 units ahead, and you keep finding everything is full, and then you come back to the starting location, because then you were not going to able to insert the element at all, because maybe all of these elements that you looked at were all full, but the other elements in the table, the other locations in the table were empty. So you somehow want that you don't cycle back. But when will you cycle back? When your offset divides the size of the table. So if the size of your table was a prime number, then your offset would never divide it, and so you would this kind of a thing would never happen. In fact, you would look at all the elements of the table then. So this is a small fact you can go back and prove, that if m is prime, then I've given you the rough argument for why this is the case, but you can also prove it more formally. This has some of the same advantages and disadvantages as linear probing. One, it distributes keys more uniformly, because now you don't form those clusters anymore. Those clusters were getting formed because you were just going one step at a time. Now if for some key you are going maybe 7 steps ahead, and for some other key you are going 13 steps ahead, some other key you are going 2 steps ahead, then these clusters are not getting formed anymore, right? And that makes the performance better. So we'll see an example. Okay, I have two hash functions h1 and h2. h1 is the same as before, k mod 13. The elements are also the same as before. We have a table of size 13. h2k is my second hash function and is 8 minus k mod 8. Yeah, so it will always be a number between 1 and between, no, it cannot be 0, because k mod 8, lies between 0 and 7. So it is between 1 and 8. 0 does not make any sense, right? If it is 0, then we are in trouble. If h2k is 0 for some k, then that means that you are continuing looking at the same place, and if that place were occupied, then you cannot insert the element at all. Okay, so let's insert the first element, 18. 18 mod 13 is 5. So it will go to location 5. Yeah. 41 mod 13 is 2, so it goes to location 2. 22 mod 13 is 9, goes to location 9. 44 mod 13 is 5. So it tries to go to location 5, but location 5 is already occupied. Yeah. So now we have to compute h2 of 44. What is h2 of 44? 8 minus 44 mod 8. 44 mod 8 is 4. So 8 minus 4 is 4. So I have to go 4 steps ahead. So I'll go to location 9. Yeah. But that's also occupied. So I'll go to location 0. That's empty. So our 44 will go to location 0. 59 mod 13 is 7. So 59 would go to location 7. 32 mod 13 is 6. So 32 would go to location 6. 31 mod 13 is 5. So we go to location 5. Now that's occupied. So I compute h2 of 31. h2 of 31 is 31 mod 8 is 7. So 8 minus 7 is 1. So 31 will now go to, we'll check 6. 6 is also occupied. So we'll have to go to 7. 7 is also occupied. We'll go to 8. And this is not occupied, so 31 goes to 8. 73 mod 13 is 8. So it will try to go to 8. That's occupied. So we compute h2 of 73. 73 mod 8 is 1. So h2 of 73 is 7. So we will go to 8 plus 7, 15. 15 is 2 mod 13. So we go to location 2. That's occupied. So 2 plus 7, 9. That's also occupied. 9 plus 7, 16. 16 mod 13 is 3. So it goes to this location which is unoccupied. So it ends up here. Right? So this is how the elements would be distributed in the table. Is this clear to everyone? So now we will do some analysis of this technique of double hashing. So recall I am going to assume that the load factor is less than 1. What was the load factor? The number of elements divided by the size of the hash table, n by n. That is less than 1. I need it to be less than 1, otherwise more than 1 does not make any sense. We are talking of a scheme where all the elements have to sit inside the hash table. Okay, and now we are also going to assume, so this is similar to the assumption that we made in the last class, that every time I probe, I actually look at a random element in the hash table, uniformly random. So the first time I probe, I will take a random element, random location in the hash table, sorry, and put the element there, try to put the element there. If it is occupied, then what do? Once again, I'll pick a random location in the hash table and try to put it there. And if that is also occupied, I'll once again pick a random location in the hash table and try to put the element there. And let's see how this performs, because we will only be able to analyze such a scheme because the other schemes are too dependent upon the hash function that we are using, right? And we might not be able to analyze that. So if alpha is the load factor of the table, then that means that 1 minus alpha fraction of the table is empty, right? If alpha is half, that means the number of elements divided by the size of the table is half, which means only half the table is occupied, so half the table is empty. So 1 minus alpha fraction of the table is empty. If 1 minus alpha fraction of the table is empty, then suppose my search was an unsuccessful search. What does an unsuccessful search mean? That the element is not in the table. When does an unsuccessful search stop? When I get an empty location. So before, how many probes will be required before I get to an empty location? right? So 1 minus alpha fraction of the table is empty. So let's say 1/10 of the table is empty. Yeah, 90% of a table is full, and 1/10 of it is 10% of it is empty. So expected number of probes required before I hit one of those 10 locations, 1/10 fraction of the table which is empty would be roughly 10. Yeah, because the first time I will maybe with 9/10 probability I will get to an occupied location, and so on and on. So roughly after 10 trials I will hit a empty location, because only 1/10 of the table is empty. So if 1 minus alpha fraction of the table is empty, then roughly 1 over 1 in an expected sense 1 over 1 minus alpha probes are required before I hit an empty location and declare it to be an unsuccessful search. Yeah. So this is the expected number of probes required for an unsuccessful search. Okay, let's look at a successful search now. Right? Now here I am going to talk about the average number of probes required for a successful search. Not for one particular search, but if I were to look at all the successful searches. So what are successful searches? Successful searches are searches corresponding to the elements in the table. Yeah, I have some number of elements in the table. Let's say I search for one of the first element. Then how many probes are required? Suppose I search for the second element. How many probes are required, and so on and on. And I'll take their average. Right? Let me try and compute this quantity. So if you recall from the last class, the average number of probes required for a successful search is the average number of probes required to insert those elements, right? Because when we were inserting those elements, we were doing essentially the same thing. Yeah, so it's the same as the average number of probes required to insert all these elements, and this is the quantity I'm going to compute. What is the average number of probes required to insert all the elements that I have in the table? So let's see. When I'm inserting an element, I need to find an empty location again. Yeah. Now suppose my table is, I began with an empty table, and I am looking at the number of probes required to insert the first m by 2 elements. Right? Size of the table is m. First m by, let's assume m is 100. I'm talking of inserting the first 50 elements. Right? Suppose I've already inserted 48, 49 elements. When I'm trying to insert the 50th element, what is the expected number of probes that are required? Right? Half of the table is empty. So when I try once, I'll maybe hit a full location. Maybe when I try again, in expectation, I'll just need 2 probes to be able to insert this 50th element. For the other first 49 elements, I might on an average even require less. But all I can say for sure is that the average number of probes required for inserting these elements is less than or equal to 2. And how many elements am I inserting? M by 2 elements. So the total number of probes required is less than or equal to m for these on average, for these first m by 2 elements. Okay, when I show you the rest, you will understand why I am doing it this way. Now let's look at, suppose I have already inserted m by 2 elements into my table, and I am now trying to insert the next m by 4 elements into my table. Right? When I am trying to insert the next m by 4 element, just assume that I've already inserted m by 4 minus 1, and I'm now trying to insert this last element. When I'm trying to insert this last element, how much of the table is already full? 3/4 of the table roughly is already full. Yeah, only a quarter of the table is empty, only 1/4 of the table is empty. So on an average, I'm going to require about 4 probes before I get to one of the empty locations. After all, I'm searching for an empty location to put this element in. Right? So I need roughly 4 probes. So in fact, I'm just placing this as an upper bound. I need at most 4 probes to insert all of these m by 4 elements. And so the total number of probes required to insert these m by 4 elements is m by 4 times 4, which is no more than m. Right? Similarly, for these next m by 8 elements, when I'm trying to insert this last of these m by 8 elements, only 1/8 of the table is empty. Yeah, and so on an average, I require about 8 probes before I can get to one of those empty locations. And so for these m by 8 elements, I would not have required, for any one of them, I would not have required more than 8 probes. I would have required between 4 and 8 probes for these m by 8 elements. Right? Because when I was inserting the first of these m by 8 elements, only 3/4 of the table was full, 1/4 of it was empty. Yeah, but I'm just upper bounding it. I'm just saying, let's say no more than 8. Okay, so just let's see what this means. So the total number of probes required to insert m by 2 plus m by 4 plus m by 8 plus so on up to m by 2 to the I. What is the total number of probes required? For this, recall from the previous slide, I said m. For this also I said m. For this also I said m. So what is the total required for these guys? M into I, because this is just 2 to the I. This is 2 to the 3, 2 to the 2, right? So each one of them is m. So it's m times I. And the total number of probes required to insert, after I have inserted all of these elements, how many locations are empty in the table? What is the total number of elements in the table now? Okay, after I inserted m by 2 elements, what part of the table was empty? What fraction of the table was empty? Half. After I inserted m by 2 plus m by 4, how much of the table was empty? 1 by 4. So it's really this last number here. After I inserted this much, how much was empty? 1 by 8. So after I inserted all of this, how much was empty? 1 by 2 to the I, which is 2 to the minus I fraction that was empty. Yeah? Okay. So after I've inserted all of these fractions, I have only 1 by 2 to the I fraction of the table empty, and the total number of probes required to insert these elements is m times I. Right? So number of probes required. Now what do we want? We have a load factor of alpha. We have already inserted enough elements so that the load factor is alpha. When the load factor is alpha, 1 minus alpha fraction of the table is empty. Yeah. So if I have to have 1 minus alpha fraction of the table empty, then how many probes are required? If I have to have 2 to the minus I fraction of the probes of the table empty, then I require m into I probes. What is I? I is basically log of this quantity, minus log of this quantity. So if I need to have 1 minus alpha fraction empty, so I just need minus log of 1 minus alpha times m. These are the number of probes required. Yeah, I've just gone from here to here. If I have 2 to the minus I fraction empty, 2 to the I is minus I is a number smaller than 1. So if this fraction is empty, then to get to this point where only 2 to the minus I fraction was empty, I required m into I probes. So to get to a point where 1 minus alpha fraction was empty, I need so many probes. Yeah. So the average number of probes required. So this was the total number of probes required. So average was just divided by n. M by n was alpha. So or m by n was 1 by alpha. N by m was alpha. So this is this quantity. So we will now be able to capture it into a table, right? So for unsuccessful and successful probes, when we had chaining, it was 1 plus alpha, recall. Right? For probing, for an unsuccessful search, it was 1 over 1 minus alpha, and for a successful search, what I just showed you, it is 1 by alpha times log of 1 over 1 minus alpha.
In this question, I have given you some pseudocode similar to what Naveen has discussed for this open addressing scheme, right? And open addressing, we know that if the table size is n, the hash table size is n, and hk is your hash for a given key k, and pkx is your probing function. Okay, so you need the probing function when if we look into this algorithm, that you first compute the hash of your key, and you want it to be less than the size of the table, so you take a mod n, and then this is your index to go into the table, right? You use that hash value. But now, as Naveen said, that if this position in the table is not null, then you cannot insert your key value pair there. So what you need to do is you need to find a different index now, and for this you need your probing function, right? Where to probe next. So you will take your original this key hash, and then you will probe using your pkx, and then the whole sum again you have to do a mod n, so that your probe doesn't go somewhere else outside the table, right? And then you increment your x variable, and this while loop goes on till you find an empty position, at the end of which you insert your value. So this is some generic algorithm for probing. Now suppose I have a specific probing function. Okay, I have a linear probing scheme where my what Naveen was discussing is always search the next position, right? But I can I can have any kind of a linear probing. So here I am jumping by 3, right? So I am doing this, I have a probing function ax and a equal to 3, okay? And for suppose for some key my hash value is 4 and my table size is 9. The problem I am facing right now with this kind of an algorithm is when I am doing this going iteration by iteration, I do the probing, right? So I end up getting this index values as 471 and then it cycles to 471 again and 471 again, okay? So the rest of the table 0, 2, 3, 5, 6, 8 are never searched, okay? And if 471 are occupied, then I will be caught in this infinite loop, never to be able to insert something, right? Though my other positions are empty. So the question I have for you is, can you choose a better value for A so that this kind of cyclic infinite loops don't occur? And based on this thinking exercise, can you also try to comment on how this A and the size of the table n should typically be related?